Good afternoon, everybody. This is RubyConf 2013. Yeah. So before we get started, we just want to say a very special thank you to the organizers of Ruby Central and to all the conference staff, the sponsors, and to all of you for being here. Thank you so very much. Let's give a big round of applause for everybody. So I am Dead Program, aka Ron Evans in the real world. I'm the ringleader of the hybrid group. This other guy over here is AD Zankich, aka Adrian Zankich. He's the serious programming guy at the hybrid group. So he does all the work and I take all the credit. Yeah. I love how that gets applause. So we're with the hybrid group. We are a software development consultancy based in sunny Los Angeles, California. And among other things, we are the creators of Kids Ruby. How did you guys like my new boss this morning? She's awesome, right? The funny part is you're kidding. You think I'm kidding. Yeah. So, but here today, we are here to talk to you about Ruby on robots. This robot is not with us today. So let me ask you, is innovation dead? I mean, William Gibson said the future is already here. It's just not very evenly distributed. Isn't that really true? I mean, many of us have been doing web development for years, and yet we've been seeing a very interesting thing happening as we've been creating all these different technologies. We've discovered that innovating is really hard. I mean, doing something genuinely different. And in fact, it's especially hard when you're dealing with hardware. So about 6 years ago, my younger brother Damon and I started building unmanned aerial vehicles using Ruby. A number of people remember that. And we had to source parts from literally all over the globe, aka China. And they would ship at these really amazing microcontrollers, and we would put them in blimps, and they would burn up, and we would order more. Nowadays, though, you can go to the Apple Store and buy several different kinds of robots. I mean, the robot revolution is already here. So we're here to introduce to you Artoo, which is Ruby on robots. It is a Ruby framework for robotics and physical computing. It supports multiple hardware devices, different hardware devices, and multiple hardware devices at the same time. In Ruby? I mean, are we serious? Yes, we are extremely serious. And the reason for that is a remarkable piece of technology called Celluloid. Tony, are you here by any chance? You bailed on my talk? What's up with that? So anyway, a bunch of the committers from Celluloid are here. And actually, this is probably one of the most important technologies to occur in the entire Ruby community in years. And if you're not paying attention to this, you need to be. In fact, you're probably using it right now if you use Sidekick, which is another great project. So it runs on the MRI Ruby, of course. It runs far better, however, on JRuby, thanks to the concurrency of the JVM. Excellent piece of software. You probably saw Charles and Tom's talk earlier. Great work. But we're going to be showing most of our demos today on Rubinius, the Ruby of the future. If you love any of these projects, please go help them. Brian Shirai is here. Brian, are you here? He's probably with his daughter. Where are all my friends? Anyway, these... I'll be your friend. Aw, giant hugs. Channeling my inner tender love. So anyway, this is an amazing project. It just reached the 2.0 release, and Rubinius X has been announced. There's really exciting things happening to it, and it's an important part of, really a pillar of the future of Ruby. Anyway, back to Artoo. So Artoo is to robotics like Rails is to web development. I'm going to say that again because it's really, really important. Artoo is to robotics like Rails is to web development. Actually, it might be a little bit more like Sinatra, as you can tell from this code example. So we see, first of all, we require Artoo. Then we're going to declare a connection to an Arduino that's going to use an adapter called Fermata, which is a serial protocol that you can use to communicate with various Arduinos and Arduino-compatible microcontrollers. Then we're going to connect on a particular port. Then we're going to declare a device. This device is an LED. It's going to use the LED driver and be connected to pin 13. Then the work that we're going to do is every 1 second, we're going to LED.toggle, which is going to turn the LED either on or off. So this is kind of the canonical make an LED blink. So we'll show you that in a minute. So Artoo's architecture, we have a couple of very important design patterns that we're utilizing within Artoo. Here's a little bit of an outline. So the main entity in Artoo is, of course, the robot. And we have two things underneath that. We have the connections, as you saw before, and we have devices. Now, we are using the adapter pattern in both of these cases. So connections use an adapter. We can use, similar to the way Active Record or other ORMs work, we can actually use these different adapters to talk to different kinds of hardware. So where connections control how we actually communicate whatever protocols with the device, then the devices control behaviors. LEDs know how to blink, drones know how to fly, etc. And then we are also using the publish and subscribe pattern via events. Devices, via their drivers, can detect events and then tell the robot about them. So it also has an API in Artoo. I mean, what good is a robot unless you can control it via an API across the intertubes, right? So here's an example of both a RESTful API and a WebSockets API that could be used by two different applications to talk to the MCP, or the Master Control Program, which will then control all of the different robots. And there you have it. Of course, test-driven robotics is very, very important. I mean, we are Rubyists, and we test first, right? Well, traditionally in robotics, the way you do testing is you would turn on the robot and jump back really fast. I have scars. However, this is Ruby, and we can do a little better. Here's an example of TDR, or test-driven robotics, as we call it. In this case, we're actually using Minispec, we're using Mocha, and we are using TimeCop. So let's take a quick look. First, we're going to declare start right now. The robot is going to be the main robot, which is, as you'll remember, very similar to the Sinatra syntax. And then before this test, we're going to TimeCop travel to the start. Then we start our robot's work. It must roll every 3 seconds. So we travel to 3 seconds after the start. We are going to expect a roll command, and then we process messages to give Celluloid's mailboxes a chance to catch up with its actors. So this way, we do not have to wait just a little over 3 seconds to test something that takes 3 seconds. Because otherwise, if we wanted to test something like turn the sprinklers on once a week, we would have to wait a week. That's not good. You think your CI is bad. Try it with robots. So of course, Artoo also has a command line interface, because one of the important patterns that we've discovered, as we call it robot ops, is that you definitely want to use commands to connect to all the devices. You do not want to do these sort of things manually. Anyway, though, I've done enough talking. How about a demo? You guys want to see a demo? All right. So the first thing we're going to take a look at is the Digispark microcontroller. So the Digispark is what we might call the minimum viable microcontroller. Oh, yeah, please. It's very small. We have to get very close. Oh, we help if you had the camera. All right, so this is it. It's extremely small. Oh, can't see it. I can see it. Move to monitor 2. Hey, there it is. So this is it. It's a rather small device, as you can tell. It actually, let's take the shield off. This is the Digispark itself. It's a very small, oh, thank you. It is a very small, AT-tiny powered microcontroller that actually uses another protocol called Little Wire, similar to Fermata, but it runs on even smaller microcontrollers. Are we good? All right, we're in focus. And we're going to use this LED shield that plugs into it-ish. It's better when it's over here. All right. So the program that we're going to run, nope, that's not it. That's definitely not it. OK, so the program we're going to run here is the first thing we're going to do is we're going to connect to the Digispark using the little wire adapter with the vendor and ID, since it's a USB device. We're going to connect to the board to retrieve its device info, which we're going to display on this screen that you won't be able to see. Then the LED device, we're going to, again, toggle it every second. So you see it's exactly the same code as we were using with the Arduino. See a pattern forming? All right, let's run this. Oh, right, the video. Executing code. So it should start to flash. A $3,000 lamp. All right, and you're applauding. That should be Apple. All right, so moving on. So what do you do with a flashing LED? Well, we are software developers. And of course, what we do is we check our Travis build status notifications. Yes, the build notifier is to physical computing like the blog engine was to website development. That's the thing you do. All right, so let's take a look at some code real fast. All right, so in this case, we're going to require Artoo, we're going to require Travis, we're going to connect to the Digispark and its different LEDs. Then we're going to connect to a broken repo that we've called Broken Arrow, in tradition of flying things that don't necessarily work. We're going to connect to the Travis repo. Then every 10 seconds, we're going to check the repo. If the repo is green, we're going to turn on the green LED. When we're testing it, it's going to turn blue when we check either the build is running or we're checking the Travis status. And then if the build fails, we're going to turn red. And then last, we have a couple of functions. One turns on one particular LED, and the other turns them all off. All right. So if this actually works across the internets, it will turn blue that we're checking the Travis build status, and then we'll turn red since Broken Arrow is a broken build. Working. 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 Fail. Now, we could go in and fix the build, but in the interest of time, let's just move on to the next thing. All right, so what is the next thing? Oh, yes. So one of the greatest things on the internet are cats. And the only thing better than cats are internet-enabled cats. For example, internet-enabled cat toys. So in this case, we have a cool little device that we've made, kind of homebrew, but we like it. It's got 2 servos, and it plugs into the Digispark, and then is connected to this fun little toy. Let's get the right angle. Can you guys see this okay? We don't have a cat. They wouldn't let us bring one in. We have a robot cat, but not the same. All right, so let's take a look at the code. Wait, that's something else. Where is the code? Oh, I forgot to load it. All right, well, in any case, we're using this leap motion. Yes, this leap motion is going to allow us to, with nothing more than his hand waves, control these servos, moving this cat toy to the invisible internet cat on the other side. Oh, wait. Can't see the toy.
Well, it's this.
All right. We broke it. I don't know how long this would last with a real cat, but it's still cool. Look, Ma, just hands. Thank you. Okay, so now let's switch to something else, the Beaglebone Black. So one of the important robot ops patterns that we want to share with you is you do not want to think you are going to develop robotics on your notebook computer unless you plan on duct taping it to a drone, which you might try. It might work for you. On the other hand, there are amazing single board system on chip or SoC Linux computers that are very, very inexpensive. The Raspberry Pi is one. Another one, though, that is a little bit more powerful but is also open source hardware is the Beaglebone Black. Where's my video? There we go. So the Beaglebone Black is a very, very cool, also ARM Cortex powered single board computer. It has a 1 gigahertz processor and 512 megabytes of RAM. In this particular case, we are running an Arch Linux distro that we have built that is also available on the Artoo, a link from the Artoo.io website, where it includes everything you're going to need software-wise to turn this into a complete, full physical computing and robotics platform. Can you see this okay? Yeah, we need it on the other side. Okay, so let's take a closer look. It's naked. We have cases, but so you see that it has a lot of different pins that you can plug into for digital I/O, for analog I/O, for pulse width modulation, and for I2C. Now, I might mention, you saw before that we had difference between drivers and connections. Well, we have generic drivers for general purpose I/O and for I2C devices. So you can actually use these same drivers on an Arduino, on a Raspberry Pi, on the Beaglebone Black, on the Digispark, or on any other platform that supports Linux GPIO. think about that. It's kind of fun. So what we're going to do here is we're going to show our, there we go, the Blink program that we showed before with a slightly different syntax, but same idea, except in this case we're going to use the connection to the Beaglebone using the Beaglebone's adapter, and we have a slightly different pin numbering scheme because the Beaglebone Black's pins are different in similar fashion the Raspberry Pi pins. This is actually what the pin is labeled on the device. That way you're not trying to go to a lookup table. I mean, there's software for that. It's called Artoo. All right, back to the camera. So now we're going to, he's actually SSH'd in to this Unix computer and is going to make our gigantic LED start flashing, if all goes well. Blink on the Beaglebone. Yes, it's real. All right, so that was cool, but can we get a little more exciting? Like, yes. So let's bring in another toy, another robotic device, the Sphero. So the Sphero is from Robotics. Yeah, the camera. The camera. So the Sphero is a small robotic sphere from Robotics based out of Boulder, Colorado. Fantastically interesting toy. It might be the minimum viable robot because it actually possesses input. It has accelerometers that can detect collisions. It has output. It can change its color. And it can move around on its own volition. It is a Bluetooth device. So we're going to connect up to it using another Artoo program, which let me show you the code for that. All right, so in this case, we're going to require Artoo. We're going to make a connection to the Sphero using the Sphero adapter on a particular IP address. Another one of the lessons from the Robot Ops toolbook is you definitely want to use serial to socket connections. You don't want to try to connect directly to serial ports. You know, that way we can use nice TCP and UDP kind of style software development. In this case, the work that we're going to do is every 1 second, we're going to display a little message, and then we're going to set the Sphero's color to a random color, RGB color, and then we're going to roll at a speed of 90 in a random direction. Crazy Sphero. So let's go and see what happens. So blue means we're connected to the Bluetooth device. Oh, by the way, we are running this off of the Beaglebone Black as well. Go, go, Sphero. It is alive. So one thing we did want to mention before we go any further is choose your own hardware adventure. What good is this stuff if you don't have some hardware? Well, luckily, we have a lot of wonderful friends. And these friends said, please give away hardware to the awesome Ruby community. So you get to choose your own hardware adventure. Now, not everyone is going to get hardware today. Only those who go to the Twitterverse and appeal to the magnificence of the robotic overlords and say, please give me a microcontroller. So if you tweet Digistump and R2IO, you can win one of our R2 Digispark starter kits that comes with the microcontroller. It comes with an RGB LED shield. It comes with all the little connectors that you will need to connect it to motors or servos or other things. So Digistump and R2IO to win a Digispark starter kit. If you want to win a Beaglebone Black starter kit that includes a Beaglebone Black, SD card, jumpers, breadboard, everything you need to build your own robot, tweet beagleboard.org, kind of long, sorry, and R2IO to win that. And if you want to win a Sphero 2.0, the hot new item, then you tweet Go Sphero and R2IO. All right, so to run through that again, Digisbump and R2IO to win that, beagleboard.org and R2IO if you go in that direction, and if you go north, you get to try to win a Go Sphero and R2IO. So again, our criteria is whichever tweet we like most. So beg, it's okay. All right, on to the demo. So Conway's game of life. Who knows about Conway's game of life? A decent percentage, but let's just do a quick mathematical review. So John Conway was a mathematician who invented something that we call cellular automata. It basically says by using very, very simple algorithm, we can get interesting emergent behaviors, essentially kind of like a swarm of robots. And we thought, let's just do the rules here real fast. So it's usually played on graph paper, using a paper and pencil. By the way, I highly recommend graph paper for doing creative work. It's fantastic. All right. So with graph paper, you would draw some cells, which are the dots. And then the rules are, if a cell has less than 2 neighbors, it dies on the next turn. If a cell has exactly 2 neighbors, an empty space, a new cell is born into it. And if where a cell is, there are more than 3 neighbors, it dies from overpopulation. So that would be the second move. So first move, second move, and so on. Well, we thought it would be really cool to do Conway's game of life with robots. But we realized we'd have to do things a little tiny bit differently. One of the differences is that the Sphero does not possess the ability, you might want to start connecting. The Sphero does not possess the ability to see other Spheros. However, it does have an accelerometer to detect collisions. So by doing a little bit of an inverse Fourier transform, we can basically turn the collisions into an estimation of the proximity within a slice of time, and thereby we can make a decision about whether or not this is actually collided and whether it should live or die. So let's watch artificial life with Artoo and Sphero. And begins. They have become alive. Now they're wandering around looking for love in all the wrong places. They need just a little contact. Not human, Sphero. Actually, human contact would probably work, but... Oh, 2 died. I feel traumatized, even when artificial life loses it. They can come back to life. We call that zombie mode. And eventually they might all die, or it might just go on for long periods of time. It's very hard for me to kill off any life form, artificial or natural. So let's give it a brief moment. Oh. It's a lonely, the last Sphero. There's something kind of epic. Maybe someone will compose a ballad. Ooh! Anyway, I think you guys kind of get the idea. Let's take a quick look at some code. So in this case, we're actually using Artoo's modular mode. So we're declaring a class, which is the Conway Sphero robot. So it's connecting to a Sphero. The device is a Sphero. The work it's going to do is first it's born. Then on a Sphero's collision, and here we see an example of Artoo's evented syntax. On a collision, we're going to call the contact method. Every 3 seconds, we're going to make a movement if we're alive, and every 10 seconds, a birthday if we're still alive. Life is short, hard, and colorful in Spheroland. So then you see some of our helpers. Check if we're alive, rebirth. If we actually follow the rules, we can be born, life, and death. So you kind of get the idea. Oh, wait, there's one last thing that's kind of important here. So then we declare a hash with all of our different IP addresses and the names of the Spheros, and then each Sphero we create a new one and then tell all of them to go to work at the same time. A swarm of Spheros. All right. So now let's do something completely different. This is the time to put on your protective gear if you have some. So we're going to demo the AR drone. And we're moving over there so we have some space. Oh, yeah, we forgot to set this up before. Whoops. Oh, the Sphero. I mean, sorry, the AR drone. Yeah, that thing. So many people got to see Jim Wyrick's Argus gem. We're actually using the Argus gem wrapped up inside of the Artoo AR drone adapter, and we've done a few contributions to it ourselves. It's very, very cool. Thank you, Jim. We really appreciate it. Standing on the shoulders of giants is awesome. All right. So what we're going to do here is take a quick look at some code. All right. So in this case, we're going to require Artoo. We're going to make a connection to the AR drone via its adapter. The device is going to be the drone. You're seeing a pattern forming. So the work we're going to do is first we're going to start the drone. Then the drone is going to take off. After 15 seconds, it's going to hover and land. And then after 20 seconds, stop. So a little bit of automated drone flight. So this is the drone. Hello. AR drone and Artoo. So now, for this next demonstration, we're going to need a courageous volunteer from our studio audience. I mean courageous. Like, this is kind of dangerous. And you have to be tall. Oh, yeah, let's just use one of the hybrid group members because I believe we are insured for them. And if not, I can just drive them home. Daniel Fisher, hybrid group strongman. All right. Oh, okay. Yes, thank you. All right, so what we're going to do, recently we added, there we go. Recently we added OpenCV support to Artoo. If you're not familiar with it, OpenCV is probably the most important computer vision library. It's open source. It's a very deep and rich platform. And so what we're going to do here is we're going to make a connection to the capture device. Then we're going to make a connection to the video device. And we're going to make a connection to the AR drone. We're going to use a facial recognition set of data. And then the work that we're going to do is we're going to capture each frame and display it on a window, which we'll see in a moment. We're going to start the drone and take off. After 8 seconds, it's going to boost up to about facehugger level. After 10 seconds, it will hover again. And then at the mysterious 13-second mark, it will begin its facial recognition mission. It should detect Daniel's face. And then as he tries to evade it, it should follow him. I think you see now why we chose our own volunteer. All right, so without further risk to us, because it's going to be over there. Get behind me, man. All right. This is how you know it's real. We swear. All right. Want to enlarge the window, please? Well, when we say customer service drone, we mean customer service drone. Evasive. We put in code to stop it before it got too dangerous. So, thank you, Daniel. I owe you a drink, man. All right. So we promise new hardware every time we do a show. And basically, we cannot disappoint. So why is it getting dark? Oh, that explains it. I'm like, it's all getting dark in here. Around the edges, especially. So we have some really awesome new hardware. Where is it? It's really small, so it's hard to find. Oh, okay, yeah, let's do that first. All right. Actually, we do have two kinds of new hardware today. So the first thing is, many of you might have seen us fly the AR drone around with a Wii Classic controller using an Arduino. But even Nintendo has stopped dealing with the Wii. So we thought, hey, it's time to get into the modern generation. So we now support the PS3 controller and the Xbox 360 controller. So Adrian, who is serious programming guy and test pilot, is going to use this generic GameStop PS3 style controller to fly this AR drone around. Let's see do I have the code here? No, I went the wrong way. There we go. So we can see that we're going to declare a connection to the AR drone. We're going to declare the device of the drone, a connection to the joystick, and then we see that we're going to, we're going to handle a bunch of these controller events. For example, when he hits the square button, it will take off. The triangle button, it will hover. The X button, it will land, etc. And so now if all goes as expected, yes, reset the drone. If it comes really close to you, please duck. This is human-powered flight, so blame him.
I just work for this guy. Don't
No, it all comes here. Blame me. I have Band-Aids, I think. Standing by. This is Tower. How you doing, Control? Still trying to connect to the Wi-Fi on the drone. We're standing by, ground control. There's a certain cadence to this. If you don't do it right, it literally won't take off. I mean, if you don't say it right. If there's anybody from Rocket City here, please correct my English. American.
All right, ready?
Standing by. Yeah, get some altitude. Get some altitude. AR drone PS3 controller. Oh, you're not going to buzz the back row? No, don't do it. Don't do it. If I want you to. It's tempting, but no, not today. Okay, so now, the grand finale. What you've all been waiting for. The Crazyflie AR drone and PS3 controller. So what is the Crazyflie? Are we crazy? We are. Extremely, if you haven't noticed that. It's probably the minimum viable quadcopter. This is the Crazyflie from BitCrazy out of Sweden. It's a, it's going to hurt, yeah. It's really small, how bad can it hurt? So this is actually a very, very impressive piece of technology. It also has an ARM Cortex processor running a real-time operating system. It's got a accelerometer, 3-axis accelerometer. It's got a magnetometer, A-to-A compass, and it also has a barometer for altitude detection. It's actually quite an acrobatic drone. It's very, very hard to control. Luckily, it's very small. Also, luckily, it only has about a 7-minute lifespan on that battery. So there's that. If you can get away from it for 6.5 minutes, you're fine. Actually, in about 5 minutes, the sensors start going off. So if you throw some like tinfoil and run that way. All right. So what we're going to do, the first time ever anywhere seen, is we're actually going to control both of these drones with the same code, which let's take a look at it. All right. So first, we're going to require Artoo. Then we're going to make a connection to the Crazyflie using its adapter. And we're going to then connect to the joystick. Then we're going to connect to the AR drone. So the work that we're going to actually do here is we're going to use the controller to control the Crazyflie. And then we're going to use the AR drone to do automated takeoff. And if this all goes as expected, the AR drone should take off and hover, and then Adrian should be able to kind of fly around it manually using the Crazyflie. Should be interesting. Let's do it. Standing by. Multi-drone. 2 drones, 1 code. They live. We so crazy. Adrian, our test pilot. Was that fun? Yeah. I love this stuff. Yeah, let's. The question was, is it possible to control them both with one controller? The answer is yes. However, because there's a significantly different vector of thrust in the Crazyflie versus the AR drone, we didn't really have time to get that perfected with the amount of space we had in the hotel room here. And we kind of didn't want to spoil all the surprise, because as soon as you start flying something around, people start coming in and swarming on it. So we'll get to that. Come and see us at Robots Conf in December here back in Florida. But wait, there's more. There's always more. We heard that some people really, really like JavaScript these days, and so we thought we'd like to put some robots on JavaScript. So Cylon.js is a project we just announced last month, and it lets you use CoffeeScript or JavaScript with Node.js to do basically the same exact thing that you just saw, except in those languages. And so it's actually available now. It doesn't have all 12 platforms supported that Artoo does, but we're getting there. And then today we announced GoBots. Because we heard that the Go programming language was something you guys were kind of interested in too, and we sort of liked it ourselves. And we thought, go robot. So actually, GoBot is this month's project announcement. It's literally very, very hot and fresh. In other words, it barely works, but it kind of does. And exactly. We have artificial life with GoBot already. So check it out. Join the robot evolution, because we need all of you to help us build this future. So Artoo.io, or follow us at Artoo.io on Twitter. CylonJS.com, or follow us at CylonJS on Twitter. Or Gobot.io, and follow us at Gobot.io on Twitter. So once again, those numbers again: Artoo.io, CylonJS, and Gobot.io. All right. So I, for one, say welcome to the machines. But there are a few questions that we have. One of them perhaps has to do with robot economics. So when machines are doing the jobs that humans do now, what will we do? Kurt Vonnegut in Player Piano kind of posited a future where the satisfaction that we have would be greatly lacking because of a meaning and purpose that we needed in our lives. And what about the pay that people need for jobs? And what about robot ethics? Do robots actually have ethics, or do they only have the ethics that we give to them? So what is going to happen? The answer is, I don't know. However, I know some actual professional futurists. And Daniel Rasmus is a very dear friend of mine. He wrote a great book called Listening to the Future, where he talks about something called scenario analysis. So we're going to do a little scenario analysis of what we think is going to happen. And we're going to use two axes. The first one is robot sentience. Will they become intelligent or not? And the other one is robot friendliness. Will they be friendly or hostile? And because we are a Los Angeles-based company at Hybrid Group, we look at everything in terms of Hollywood movies. So if the robots become not intelligent and they're not friendly, we get the movie Brazil. In other words, life today. Now, if the robots become intelligent but they're not friendly, we get Terminator. Enough said. Now, if the robots are not sentient but friendly, we get Power Rangers. And then, if the robots are both sentient and friendly, we get Singularity. So this guy spent a lot of time thinking about what was going to happen in the future. I hope everyone knows that this is Isaac Asimov. You didn't know Conway's Game of Life, but thank God you know Asimov. So he wrote the 3 laws of robotics. And I'm going to read them to you now. Number 1, a robot may not injure a human being or through inaction allow a human being to come to harm. Number 2, a robot must obey the orders given to it by human beings, except where such orders would conflict with the first law. And then number 3, a robot must protect its own existence as long as such protection does not conflict with the first or second laws. So how's that been working out for us, guys? But I don't think it's fair to blame the robots, because this, in fact, is not a robot. It is a drone. And it is being controlled by a person in a hidden bunker where they are far, far away from the battlefield where these weapons are actually being utilized against real humans. So we propose a small change, just a little patch revision to Asimov's first law, version 1.1. A human may not injure a human being, or through inaction, allow a human being to come to harm. Imagine that future. Let's make that future. Thank you.